when I hear talks from the public cloud providers, I'm always amazed by the scale that they do things at. It's just incredible. So this is a really a different kind of tack. We're looking really at something that's come up from an individual community and developed a cloud environment from that kind of starting point. We've got an hour. You didn't ask many questions, so I'm hoping David's going to ask lots of questions, because if you know David well from other conferences and meetings, he's not short of questions, which is great. But please do stop me in the middle of a slide if you've got a question to ask. It actually helps me, so that would be really good. And if you don't, you'll get lots of questions from David. So, as David said, I'm from the Centre for Environmental Data Analysis. We're part of the Space Department at Rutherford Appleton Laboratory in Oxfordshire in the UK. And this is very much, it's a big effort. So I've mentioned some principal names here, but there's a big team that are underpinning this resource. So there's Jonathan Churchill there, who provides the underlying infrastructure from the Scientific Computing Department on site. So we work with them very closely. And Brian Lawrence is the director of CEDA, and he's been really the inspiration and come up with the original idea for JASMIN. So I'm just going to preface my presentation with a little diversion about an individual application that got hosted on JASMIN. So JASMIN started around about 2011, 2012. We had a second phase of renewal of investment through the NERC Big Data program. And that's where this project came from. It's EOS Cloud. And a guy called Tim Booth I worked with from CEH at Wallingford, he came to use the cloud environment, and he had this idea for providing like a desktop as a service application. So users can access a desktop like you would do on a laptop or a desktop computer, but backing that up underneath is a cloud environment with all the computing power that provides. So a really powerful concept. Now the really nice thing about this particular application is that it takes the best things about cloud, right? It uses the elasticity aspect of cloud. So David gave a great introduction about the different aspects of cloud computing and what makes something a cloud. And I think this is a really good example. So you have like a web portal that you can go to. And if you have an application that's particularly resource hungry, which apparently happens a lot in the omics community, I don't know what's wrong with them, but they write applications with loads and loads of memory. You wouldn't find that in the Earth observation community, of course, but they do have that problem. So this is great because you can log into this portal and you can borrow an extra piece of memory from a pool, from the quota that you've got allocated to your tenancy in the cloud. So an individual user can get that additional piece of memory, use it to run a memory-hungry application, and they're not interrupted at all in their use of that desktop environment. So they can use the same application, but they get access to all of that additional memory. So that's a really, really good feature. Now, it was a really nice, satisfying thing for me from the point of view of us as the infrastructure provider. When Tim approached me, it was a couple of years ago, I think it was around about September time, he said, Phil, we need to be able to expand the tenancy that you host for us on JASMIN. We need some extra memory and compute and storage. Can you do it for us? We want to run an event. And I said, yeah, okay, that's great, we can do that. So we did it. And then a few weeks later, he sent me this picture. And he'd run a workshop, I think it was in Bristol or the West Country or somewhere, where he'd used the EOS Cloud desktop as a service environment to teach a whole bunch of PhD students. And that was so good because we didn't get to hear anything about that, right? You know, he just gone on and did it. All we did was boost his quota up, and he went away and he was able to get all the resources he needed to run these simultaneous desktop environments for these students and use it for a training event. So I think that's a really good example of how cloud is like a game changer that Dean was talking about. You know, it's really a disruptive technology, and it's bringing things that we just wouldn't have been able to do before. So, what about JASMIN then? So my colleague Matt Pritchard has this picture of it's like a restaurant or something, or a takeaway, JASMIN. The idea is that researchers and scientists can come and use this resource and host their applications, get access to data, and use it in a way that's a very informal approach, where they can run their applications, get the results, and then move on and do something else. So I'm going to talk about the origins for the environment, how we came to build this system. And it's really around the challenges that we've been seeing, and I'm sure it's true of many other research domains as well, over the last 10 years, and how JASMIN was created to address those. A bit about the technical solution, some analysis of the current usage of JASMIN, some particular exemplar projects focusing on cloud, of course, and the role of training and outreach, which I think gets overlooked so much of the time. I think for a lot of people, they are nervous or uncertain about cloud computing technology. They don't know how to approach it. It's like, well, where do I start? And this whole thing of training and outreach, I think, is really vital. And then a little bit about our future plans. So you can see a picture of our machine room there with some nice shiny blue LED lights, which we're very proud of. Okay, so JASMIN, it's a bit of an awkward acronym. I don't know what the MIN stands for. I think Brian knows, but he's not telling me. So the first two letters are a joint analysis system. So it's really a focus on the data-intensive side. So it's a data-intensive computer facility tailored for a specific scientific domain. That's the environmental sciences research community. That's important. So everything that we've built, right from the bottom up to the top, has been optimized and thought of around the kind of workloads that we want to support in the environmental sciences community. As I mentioned, we're at Rutherford Appleton Lab in Oxfordshire. And it was conceived around about 2011 as a sort of coordinated national response to address significant trends that we were seeing in our domain area. There's also the facility CEMS. So I thought I should spend at least a minute or two explaining, because that was in the title of the presentation. So CEMS stands for Climate and Environmental Monitoring from Space. And what happened around 2011 was there were two programs, really, which had overlapping goals, I would say, between JASMIN and CEMS. So CEMS was trying to do some of the same things, but with a particular focus on Earth observation, but also a strong emphasis on business and on academic and industrial collaboration. So I think it's really important, the kind of things that it was aiming to do, and that actually it's continuing to do now, for this kind of audience today, because I think there's quite a few of you here from industry too. So CEMS has two components to it. There's part of it that is hosted at the Satellite Applications Catapult on the Harwell campus, just across the road from us. And we host the academic component, the part of CEMS that's to do with the research community. But in practice, there's so much overlap between the two. So we treat it as a single facility. So what about the trends and the drivers for this kind of environment? Why have we done it? There are a number of things that you could identify. I'm sure this is not the only ones. There are other things you could look at too. But there's been a huge growth in direct numerical simulation, accompanied by significant increases in simulated data. So right from, when would it be? I think it was about 2005 time, we were involved with CMIT5, the Couple Model Intercomparison Project, Phase 5, which is a bit of a mouthful. So it's a coordinated set of climate model experiments, the results of which went into the 5th assessment report on climate change through the IPCC, and went into the negotiations for governments to negotiate cuts in outputs greenhouse gases. So really important. So that's one area where I think you could see with the increase of computing power, you want to go to higher resolutions, you want to both temporally and spatially, you're producing masses of more data, you're doing different ensembles because you have different variables that you want to look at. So massive increase in the amount of data. But what's been really interesting is the increase in simulation around the Earth observation community as well. I was at the NCO meeting about 6 months ago, I think it was, and NCO is a part of the Natural Environment Research Council that looks at Earth observation, and I was really interested to see so many more presentations where people are doing simulations or they're doing reanalyses, where they're using observations and applying models. So huge growth there. As we know, there's big growth in Earth observation data through Copernicus program and the satellite missions. Increasing complexity of algorithms, the size of the teams working on data analysis as well. And there's also a need to manage and preserve increasing volumes of data from the NERC community and to help the community to manage what's a huge volume of data. You know, how do you make sense of it? How do you even discover what you want to use? And once you've discovered it, is it the right thing for you to use? So some really tough questions. So for a researcher or a scientist, it is daunting. There's too much data. We've got insufficient storage with the compute. It's difficult to share data and workflows. It's a problem which goes across institutional boundaries, right? Because if you think of an individual institution like a university, it may have a department that specializes in Earth observation or climate science, but it wouldn't justify making a facility for that university just for that domain area, right? But if we bring together all the people who are working in that domain area nationally, then we can make a facility to serve all of them, and it's tailored to that specific domain. So that's something that's really powerful to have. So the burden of curation as well is too much for individuals to take on. I think this is something that's consistently ignored, and people do not understand it. They don't understand it. That we have got a huge problem of the complexity of the data that we deal with. And scientists spend a disproportionate amount of time fiddling around with data formats and trying to get things into a form where they can actually get some productive work done. And so there's a really vital role to be played by data centers in curating and managing data and getting it into a form where scientists can actually make use of it and get some good science out of it and spend their time on science and not doing data formatting and data science. So, JASMIN's value proposition now. A data commons with enough compute to use the data. So there are a number of things, a number of ingredients there. Provide state-of-the-art storage and computational environment. Provide and populate a managed or curated data environment with the key data sets. That's our data centers, our data archive. Provide flexible methods for exploiting the computational environment, and encourage and facilitate the bringing of data and or computation alongside to the archive. So there's this huge, huge thing of data gravity. Data gravity. So if you bring data all into one place, you enable so many new things. And we're seeing this where the researchers who are coming to us are increasingly interdisciplinary, right? So if you have all these different environmental data sets in one place, you can draw users in, draw users together, and get the collective benefits of that. And there's another outcome from that as well, which is really great to see, and it builds community and collaboration. So groups are working together. They're starting to cross these different boundaries and understand the sub-disciplines more, and potentially get more out of the science. So, if you were to build computing resources for a given research activity, there's a whole trajectory for what you want to do, what you want to achieve, from investigating data to determining the analysis you want to do, to figuring out what process you want to use, to store the results, to analyze it. Now, you would ideally want something that's nice and uniform and easy to use, but the fact is that it's not like that. It's not like that. We're not there yet. You know, there are some incredible things with the public clouds, where they're making a lot of these things easier. They're providing abstractions on top of this complexity to really help. But in reality, there's a set of interacting tiers and interfaces. And this can result in uneven silos containing like sweet spots where you can be really productive and get lots of results, but other areas in the computing spectrum where it's just hard. It's not been solved yet. There are these gaps or valleys that need to be filled in. So over on the left-hand side there, I've put like a very generic schematic to show, you know, you've got the underlying physical infrastructure, the compute, the storage, and the networking. You've got virtualization and cloud computing, which can really help to abstract that and make it into a usable form. But then there's the domain-specific applications and services. It's really interesting to look at, I don't know whether you've heard of the ESA network of platforms RFI that's come out. Anybody? No? Yeah, some nodding of heads. So they're really looking at this set of tiers and looking at how different providers can come in and slot into those different areas, be it infrastructure providers, the clouds, to people who've got domain expertise in providing data or services in a particular area, or maybe somebody who's a data center who provides just access to data. So, for us, what we've got basically is our data-intensive computer facility at the bottom there. So really, I suppose that's the layer that you would consider as being like a cloud provider. But I think the difference for us is that we're building all of a stack on top of that. So we're building a domain-specific environment to serve the environmental sciences community. So we've got the CEDA archive, so key data sets, Earth observation data sets, model simulations, reanalyses. But we've also got group workspaces as well, so the ability for users to be able to output their own results and store them and provide access to their colleagues and their collaborators. And then over the top of that, we're using the cloud service model that David was talking about, using infrastructure as a service, using platform as a service, software as a service. But I would argue there is a case for virtualization, there is a case for batch compute. There are cases for bare metal. I shouldn't be saying this in a cloud talk, but there are.
Infrastructure is a panacea for every single
it isn't.
Workload. It is a distribution.
Yeah. Okay, so we can talk about that a little bit more in a few minutes. So, at risk of repeating things that have already been said here, so with infrastructure as a service, you can make your own virtual machines, your storage and your networking configuration. Software as a service, examples for us are things like a web map service, if you're familiar with the OGC standard. That's a good example. IPython notebooks, they were mentioned just before, web portals. And then platform as a service where we've got something more like a shrink-wrapped environment where you can do development and analysis. Virtualization, pre-prepared scientific analysis hosts, and batch compute where people can just run things massively parallel and get the results for processing over. Typically in the Earth observation community, it's doing reprocessing of satellite missions, that kind of use case. So the other ingredient that's really critical here is the links to the other facilities that are producing data. And it was a central tenet for JASMIN that it's predicated on this problem that HPC facilities have massive amounts of compute, but they don't have massive amounts of storage. So your researcher comes, they do their processing, and then their results are going to get kicked off, right, after a while, because they're going to run out of space. So JASMIN was part of the fundamental tenet for JASMIN was to say, okay, take the output from your HPC simulation, stick it onto JASMIN, and then you can do the secondary analysis that you need to do. So these links to UK resources are really key. So what have we seen? Over on the left-hand side, we've got the compute figures. We've really got to understand here what JASMIN's about. It's not about having lots and lots of compute. It's a data-intensive facility. So it's about having lots of storage and some compute. Okay, so the emphasis is different. But you can see in the top graph there the utilization there. And David said, if you've got HPC, if you've got batch compute that's being utilized more than 0.65, 65%, then what did you say?
Go back and ask again.
Go back and ask again. Well, we've got 70% utilization. Okay. So yeah. So there are things that we're going to be doing about that in terms of expanding, but I think it's indicative of the success of batch compute, and it stunned me as well through the evolution of JASMIN. I just didn't realise how much latent demand there would be for batch compute. We can talk about that in a few slides' time. In fact, it's the next one. And then on the right-hand side there, you've got the data storage. This is on our fast disk. And you can see the purple line is the biggest one. It's group workspaces. Okay? Access to the data archive, the curated data is really important, but people want somewhere to store their outputs. They want somewhere to store their outputs. So that's really important. And at the bottom, we can see some spikes in the graph. This is to do with number of files. And there are particular missions or projects or programs where we've had a big influx of data. And we're wondering how that's going to happen with CMIP6. Because, of course, with satellite data, you get a steady stream of information. But with the things like CMIP5 and CMIP6, you just don't know. They might come along like buses, right, when the modelling centres have got their outputs ready for publishing. So that's quite a thing to manage. Okay, some quotes about using batch compute on JASMIN. Again, it's just incredible. I remember when we first deployed the system in about 2012. I remember talking to Jonathan about the trucks arriving with the gear to install it, and he got the parallel file system up and running, and he got like 3 petabytes up and running in a day, because it's this parallel file system that just allows you to do that, and it's just really incredible. But we had a batch compute environment, and we weren't sure how it was going to work out. We just didn't know there was going to be all this latent demand for usage. And we had a group at RailSpace who were doing ATSR reprocessing, and they'd done it on their own commodity kit. They came, moved it onto JASMIN, and it was just fantastic. The guy who organised the processing, he was just stunned. He said, I can't keep up with the results. I can't keep up with the results, because it used to take a couple of months to get the full reprocessing done. It did it in about 3 days. So he was just stunned. So it's really fantastic when we have stories like that, where the science has been revolutionised, because your repeat time for doing experiments is just pushed like that, compressed, right? So your ability to investigate more things is just increased incredibly. So it's really, really great. We had, no, I won't say about that one. There's another example here. This is just drilling down into something a bit more specific. This was for the QA for ECV project at UCL. They've got a 700 terabyte workspace. That's a sizable portion of our group workspace allocation. So they've got a massive amount of storage space there. And they're using it for ECV, essential climate variable generation. And they're producing hundreds of terabytes of data. And they're able to pull data across from the States as well. So all of this these ingredients coming together have made it a real transformation for them. How much time have I got? A while yet. Okay. So I'm going to change tack now again. Halfway through. Okay, right. I'm going to change tack again and talk a little bit about the JASMIN architecture from a sort of a schematic view and the relationship between the different pieces and our use of cloud. So when we started off, we built on a very much an incremental approach. We didn't try and build everything and then hope that users would come. We felt we'd learned some lessons from experience with past projects. The experience of the eScience program and grid infrastructure, without making any judgments either way, But we felt it was really important just to build things gradually and then see how users want to use stuff and then add to that as we went along. So the first thing that we got up and running was the batch compute. And we benefited from the brilliant I/O performance and a relatively modest amount of compute, really. But it was transformational, as I say, for a core group of users who were doing reprocessing or doing analyses. So that's great, but we're only impacting on a small group. And I think the challenge for us was how could we reach a wider group of our community, those who feel intimidated about using a Linux command line, who wouldn't know how to start with a batch compute environment. It's those kind of users that we wanted to reach. And we saw cloud as being an enabler for that. And I'll try and explain a little bit about how that's worked over the next few slides. So building on top of that, what we did, we added like a parallel infrastructure next to what we call our managed environment. So in our managed environment, we've got the data archive, we've got group workspaces, we've got a batch compute system. We realized that if we were going to be able to do infrastructure as a service and do it properly, we needed a parallel system next door to the main environment. Because if you know anything about infrastructure as a service, you as the user have got a high degree of control over what you can do. You're root, right? You can make virtual machines, you can provision virtual networks, you can make your own storage. That's not something that we can put next to a managed archive. It just can't be done, right? Or at least we couldn't do it. Certainly when we were considering that in the beginning, it just wasn't going to happen. So what we did was we created a parallel network so that we've got good connectivity to the main resource, the archive and the batch compute, but it's isolated so that users can do true infrastructure as a service and make their own environments. So here's an example. Users can get a tenancy on JASMIN. They can access it through our cloud portal. And they can make their own virtual machines. We're using software-defined networking so that basically in your tenancy you have your own internal network for virtual machines, and then you can make them visible to the outside or hidden as you choose. And we started to have projects where they were doing more like batch compute, but using the virtualization, using cloud to do it. But what we also added in was the ability to make your own tenancies within our managed infrastructure as well. So this we've done as more like a platform as a service kind of operation. So rather than getting complete access to the virtual machines, the machines, you have non-privileged access, and the machines are kind of like shrink-wrapped templates for doing different tasks like scientific analysis or like a database server and that kind of thing. And if we do that, it means that we can put that environment right next to the archive with direct file system access.
What's the process for adding new templates in that area? Is there a defined process?
Yeah, because it's PAS, it has to go through us.
Right.
Yeah.
But
yeah.
there is a defined document.
Yeah. So what we're trying to do is track different use cases. So we're seeing quite a few cases where people want to do batch compute, but they want a database next to it to index their data and do that kind of thing. So there's a clear pattern there. So that's be an example where we would create a new template. Yeah. So what about the guts of our cloud system? It's built on VMware vCloud Director. We built our own portal on top of that, on top of the web service interface for vCloud. And we used a real keep it simple approach. Provide just enough functionality to provision and configure virtual machines. Really key to have the right tools for the right users. So we really encourage tenants to have like a system administrator or somebody responsible for that tenancy so that they know what they're doing, okay? Because if you're giving root access to a scientist, bad things can happen, right? Okay. Or managers, yeah, indeed. Okay, and we've tried to keep an abstraction layer for our cloud stuff as well so that we didn't get locked in. So if we wanted to move away from the VMware, we could do. We could move to OpenStack, or we can even cloud burst, right? And use Amazon or Azure or Google or somebody else. We're developing an interface for onboarding users as well. and try and make that a really simple process. So how can we use cloud to reach the long tail of science users? So I think, as I've tried to explain, the infrastructure as a service is an underpinning enabler for creation of bespoke applications hosted next to the data. And I think this is something that's still fairly nascent in the research community. You know, I think there are other communities where they're way ahead and they've been doing this for years. I think some of the bioinformaticians are doing some really, really advanced stuff, and there's some catching up to do. But there's that capability there. So different approaches have been adopted through different projects hosted on the JASMIN Infrastructure as a Service offering. There's a project from Centre for Ecology and Hydrology in Wallingford called MAGIC. And their approach was to say, okay, you've got batch compute, you want to run a complex 4-chan model, the duals land service model, let's just wrap it up in a portal, right? So you make a web portal that's hosted on our cloud environment, and it goes away and launches the model codes for you. So it's an easy-to-use interface for scientists. The NERC Environmental Research Workbench took that a little bit further in the sense that you can wrap arbitrary code. So an administrator can take a given piece of code, wrap it up into an adapter, and then integrate it into the Workbench environment so that users can come along and access that again through a web portal and launch that code and get the results they need. And then EOS Cloud that I mentioned before, desktop as a service. And then Jupyter Hub, which Dina mentioned as well on Amazon, is such a fantastic tool. It's so amazing. I'm going to talk a little bit about it about one project where we've used Jupyter Hub in a minute. So yeah, there's these various virtual research environments that we've hosted on JASMIN Cloud. And again, it's been really interesting to see the different approaches that people have been using and the interactions between different groups as well, and how we're able to learn from each other. Again, it's this data gravity thing, that if you start to have the data in one place, you get people using the data together and talking to each other and collaborating and getting better results and doing more advanced stuff because of that. Oops. Right. So I'm going to take a project called Opterad as an example of one of these virtual research environments. And it builds on top of Jupyter Hub. And the goal of it was to address this problem of producing consistent land surface information products in the EO sector out of heterogeneous Earth observation data sets. So they wanted to provide a collaborative research environment as a means to get the algorithm specialists to work more closely together, okay? Because they're working at their individual universities, they've got their own code bases that they're working on. If we could just get them to work together in one place in a shared environment, you can start to have more interaction and share code together and get some more consistency. Computing resources, they wanted to do processing at a real high spatial and temporal resolution, so they wanted something that was better than what they could do at their university or indeed on a desktop environment or a laptop. And this whole thing of usability and access, they wanted easier execution of Python code and provide something that could be used as a training resource as well to help students.
So is this a sort of social network for environmental scientists?
Not quite, I wouldn't call it that. See what you think when I've finished. So, are you all familiar with Python notebooks? Yeah, you know about it, all right. So I can skip this slide, right? You don't have to be shy or embarrassed if you don't know.
Go on, go through it.
Go through it, okay. So it's really cool. You have the ability to expose Python kernels through a web browser. And in fact, it's not just Python, it's programming languages like R as well. And sessions can be saved and shared. You've got hooks into doing parallel compute as well through the Python API. And the Jupyter notebook took the notebook as it was, which was something that did run through a web browser, but was really a single user interface, and made it into a multi-user environment. And that's really important. And it's gained traction as a teaching and collaborative tool. So this is just a perfect marriage, Jupyter plus cloud. So we know about cloud characteristics, the broad network access, the resource pooling, elasticity, scale, all of those things. It's a great fit for big data science applications. And then with the notebook as well, you've got something that you can host and make it broadly accessible to a wide community through a browser interface. There's Wikiri, Azure, Rackspace. I didn't know AWS was doing it, but yeah, I think just about everybody's got, yeah, Kenji's thumbs up there is providing notebook environments. Yeah. So it provides central hosting as well for management of software packages. So there's no installation steps needed by the user, which is, again, a really good thing. It avoids those barriers and those initial steps that many researchers have to go through before they can actually do some science. And I think it's a good potential as an algorithm prototyping, can't get my words out, prototyping environment. Because you've got access to all of this data resource, you can do analysis and try things out first, and then maybe work it up into something that's going to be, I don't know, you rewrite in Fortran, heaven forbid, or you do it in C, which is great. You can run it in a way, in a much more systematic way in a batch environment, but it provides that stepping stone to get something that's workable like that and allows you to do the experimentation and the interactive analysis. Okay, so we've got a screencast here. I'm going to try and get working. So this is something my colleague Matt Pryor did for our JASMIN conference in the summer. So it just shows you the Jupyter environment. And sorry for those of you who know it already. And I'm probably going to bore you a little bit. But you've got different notebooks that you can save and share with people. There's this JASMIN conference notebook that Matt prepared. You've got access to clusters as well, so you can do parallel compute. And let's see, what's he doing now? Yeah, so he's got a notebook where you have documentation in line with your code, which is really powerful for training and teaching. And you've got support for different languages as well. So different versions of Python even, or R, or other things. So here he's just editing some of the documentation text. He uses a really simple markup, or markdown it's called, language. And then you have these different cells where you can execute pieces of code, and there's the inevitable hello world in there. And then you can do all the normal things you can do in Python. It's got this special feature for embedding things like matplotlib for doing plots. And then here, he's taking some data from our archive. And again, we're trying to take advantage of this fact that we've got our data right next to where we're running the Python notebook environment. He's got some code there to, I think he's just going to plot, yeah, it's chlorophyll content. Okay. Chlorophyll concentration in seawater. So it's from one of our marine applications. And there you can see the plot. So it's something very noddy and straightforward, but it gives you the idea of what's possible. And then he's going on to show the iParallel interface. So this allows you to run things in parallel. He's got a simple function to calculate a mean, and that's something that obviously is very easy to parallelize, because you could take an image and cut it up into blocks and then work it out for each block in parallel and then bring the results back together, a kind of a map reducer pattern. So you can do that easily with the Python code. So this is an example of where we're trying to bridge from this model of providing batch compute, where people maybe aren't familiar with Fortran or using a Linux command line, but maybe they're happy with using Python and providing it in the JASMIN environment. I think here he's just running the same thing, but using, yeah, he's using iParallel client to run it in parallel using the cluster. it's a really noddy example, but hopefully it gives you an idea of the kind of thing that's possible. I'll mention about it a bit later, but we're really interested in looking at things like Dask. Have you come across that? Dask is like an environment for running things in parallel, where it provides an abstraction for the user, so that it's much easier for the user to take advantage of it without having to know about running your program in multiple threads or processes, all that kind of thing, but do it in a familiar Python way. I think that's it. Okay, so next slide. So this is the architecture we've used. This was done a year or two ago, so we're rethinking some of this. But we took advantage of Jupyter Hub integration with Docker and with the orchestration that comes with Docker called Swarm. And we were really surprised at that time by the maturity of Jupyter Hub, even though it was only, I think we cloned it from from Git, from the main trunk, and it just all worked. It was great. It was really bleeding edge at the time when we tried this out, but it was fantastic. So we've got these notebooks running in containers, and then we added in IPy parallel support as well at the back end, and we've got shared file space with an NFS server and user space with an LDAP as well. So this is all within a cloud tenancy, okay? So we're trying to use all the DevOps tools we can to make this self-provisioning as much as possible, tools like Ansible and Vagrant, so that we can make it easily deployable. So, there wasn't much budget for this project, but it was incredible. You could get so much out of it with so little effort, really. So the off-the-shelf solution really worked for us. Installation was straightforward. It was operationally robust. And it's a platform that's been used to host training. So in, I think it was August or September time, at ISA Esrin and Frascati in Italy, they ran a workshop for about 70 students on Earth observation data assimilation. So again, it's great. It's a bit like the EOS Cloud example. We could just talk to the tenants, make sure they had enough quota to run the workshop, and the next thing we heard was they'd done the workshop and it had been a success. So it's really fantastic. So this whole area of training and outreach is just so critical. Because you think about something like that notebook environment, unless users get at least an initial orientation with it, they're not going to be able to take advantage of it at all. Not going to be able to use it at all. So a NERC assessment, there was a 2010 one and then a refresh in 2012, where the most wanted postgraduate and professional skills were modeling, data management, and multidisciplinarity. And industry as well, regularly, I mean, you can agree or disagree with me here, there's a big demand for big data skills, and data analytics is really important. So JASMIN's providing access to the academic sector for these kind of skills. So I think it's really important for helping the UK economy and helping all of us, really. So training and outreach is really critical. We've run an NCAS, Introduction to Scientific Computing course, at least 2 times. I think it's probably more than that. I think maybe we've run it at the Met Office as well. Again, it's fascinating talking to the people who do the training and understanding where postgrads and scientists are coming from. When we initially tried it, we used the notebook environment, and some of the students, they just weren't ready for it. Even that was too complicated for them. They just needed a simple command line and type Python and do some really simple commands to get them started, and then they could start to move on to more advanced things. So we've got a graph there showing, or a bar chart showing the number of users. We've had over 100, mostly postdoc students register to use JASMIN every year, and around 2,000 more each year to exploit the data download services. I think there are about 5,000 users for the data download. So future plans, there are big challenges up ahead for us in terms of data volumes. The two main challenges for us are CMIP 6, which is the successor to the fifth coupled model intercomparison project, where we don't know how much data we're going to have. Some people are talking about 50 petabytes. I think I saw in recent material that the high-res MIP, the high-resolution model intercomparison in the European contribution is going to be 2 petabytes alone. So I think for CMIP 5 there were around about 20 modelling centres participated, so it could be potentially very big. Sentinel data you probably know already. You don't need me to tell you that it's very big, 6 petabytes a year. We've got a commitment to hold all of that data on JASMIN. And there are some challenges from a technology point of view. So it's not just the volume of data coming through. We're really starting to look at the use of global file systems. The system that we've got has been very productive. And there was one of the quotes, I don't know whether you noticed it in one of the earlier slides, but this guy said, I've taken this workload that I could have run on my desktop and I just made it bigger. Like, I just put it on steroids, right? I took the whole thing and bunged it on JASMIN and it just works, right? It just works. And the reason it works is because the environment, all the interfaces are exactly the same, right? It's using a POSIX file system. It's just massively expanded. But there are problems with it. When you have such a large system and so many users, it's really difficult to manage all the user accounts. And if you want to do true cloud, as I mentioned earlier on, if you're doing infrastructure as a service and somebody provisions their own VM, they've got root access. They can make up whatever users they like, right? So you can't expose a global file system to that kind of environment. It ain't going to work. And we know from the public cloud providers, and Amazon created S3, right? So I guess they realized very much earlier than anybody else did the need for this kind of interface. You need to have an abstraction from the data access. And so there's a big challenge for us. What are we going to do? We're going to move more towards object stores. If we do that, it means that we can scale much better, both in terms of the amount of data and in terms of adding additional storage to our environment. That's great. But for the user community, they've got to get their heads around S3 access or an S3 style interface. So it's part of my motivation for the question earlier on. That could be a big deal for some users. They're used to the POSIX interactions where you can do CD and you navigate through a hierarchical file system. S3 is not like that, right? You've got these handles to the different data, and that's it. That's all you have, okay? Very powerful, but it's a very different kind of paradigm. And we need to think about how we help scientists and researchers to be able to migrate to that. One of the things that I think's helped us from our point of view is this whole thing of NoSQL solutions, things like Elasticsearch and Apache Solr. For the Earth System Grid Federation, it's a big program of software infrastructure that was developed to support CMIP 5. It uses Apache Solr to, firstly, to index all the model outputs, so to take all the NetCDF data and to extract all the variables, index them into the NoSQL database, and then create like a powerful faceted search interface so that users can pick the different experiments, the different model centers that they're interested in downloading for, and then get to the data. But that's all dependent on the development of control vocabularies, community accepted sets of terms that everybody agrees they're going to use, and the way that they're going to organize their data in that way so that you can find it consistently across more than one place. So ESGF did a lot of work with that. I think if we're considering moving to an object store kind of paradigm, then that can help us, that kind of approach. Because whilst you don't have the hierarchical file system and a different structure in the directories, you can use something like Elasticsearch or Solr with a faceted search to find the data you want. All right? And I think as we scale up, these hierarchical file systems, they just can't cope. They can't cope. And I think as we're seeing the amount of data increase, it's increasingly important to have really good discovery services to enable you to find the data and access it. Because if you can't do that, you might as well not be there. So our plans for cloud software for the future, we've got a bit of a fork in the road here. We've got to decide what we're going to do between the VMware, continuing to use that, or to go with OpenStack. One of my other hats is that I'm chair of the cloud working group for the Research Councils UK. And we had a meeting, I think it was about 18 months, 2 years ago, where there were a group of people who were all involved in deploying private cloud infrastructure or community cloud. And we did a little straw poll and went around the room to see what kind of technology they were using. And the first one said, oh, what are you using? I was chairing the meeting, so I said, what are you using? OpenStack. Okay, all right. OpenStack. OpenStack. There are about 20 groups, and they're all using OpenStack. So there's been considerable convergence in choice of software. And I think David would know from this, from his early experiences using private cloud software, that it was a very different situation some years ago when you were first looking at it with Flesser.
So there are interesting issues that are coming up with OpenStack, and the fact you wouldn't be able to do what you do at the moment because it doesn't support the fine-grained data or NLZ.
Yeah, we can talk about that.
Findings that people are doing now with OpenStack because it's targeted towards a particular private cloud methodology.
Yeah, but it was very much more heterogeneous, I think, when you were first looking at it.
Oh,
yeah. There was Open Nebula and a whole bunch of other technologies that people were looking at.
It was still there in Europe, right?
It's still there. It's still there. Yeah, true. Software-defined networking is absolutely key to us because being scientists and researchers, we like to work together with buddies. We like to collaborate and share stuff. And this whole thing of the multi-tenancy characteristic of cloud is so powerful for the research community because it means that you can allocate a piece of resource on your cloud environment for a given community and a group to share. But if you're going to be able to do that, you need to be able to have the software-defined networking to draw a line around it, a box, and say, this is the piece of resource that this user or group is going to use. So being able to do that is really important, and I think it's one of the last frontiers with cloud computing in general. It's the thing that causes the most problems, always. Scaling elasticity, so we want to be able to scale, take advantage of cloud, increasingly for our batch compute. We've used bare metal so far. It's worked great for us, but we're going to need to rethink that, I'm sure. Also for our download services as well. We are shifting terabytes of data between different centres for our international collaborations. And we need to be able to use schemes and mechanisms to allow us to share that data effectively and to scale. I mentioned about parallel file systems. Resource monitoring and charging. That's not something that we've talked about very much so far. For us in the research community, there is the expectation that it's free, right? Research is expected to be free. They know that it's not free. You know, they're not pretending that there's not somebody paying for something somewhere. They know that. But the fact is that it's sponsored through the funding bodies like the Natural Environment Research Council, so that if somebody wants to use the resource, we use an approach where people have a proposal or they've got NERC funding, and that goes through to JASMIN, and then we make an allocation for a tenancy for them on that basis. So it can work two ways, I think. I think it's good in the sense that it gives users less sort of worry about cloud, because they're not thinking, how much is this costing me? How much is this costing me? Because they've got a fixed thing, an allocation of time. So they can relax a bit from that aspect. But nevertheless, there are cases where we need to look at our charging model and do as a pay-as-you-go, much more like a public cloud kind of way of working. So we're going to need to look at that. Federation and hybrid models are going to be important for us. I think overflowing into public clouds is a real thing we could look at for batch compute. And also for collaboration with, in a European context, things like the ESA network of platforms activity and the European Open Science Cloud. Although it's called cloud, I don't think it has anything to do with cloud. But nevertheless, there's a need for sharing and for being able to interoperate and federate things. And as David said, I think with OpenStack, you can do single sign-on with OpenStack, but you can't do the authorization. Yeah, you can do shibboleth, right, can't you?
Yeah, it's got some very funny internal structures because it's intended to be for essentially one organisation.
Yeah.
It's not a multi-tenancy support.
Yeah.
They've gone away from that.
So I think single sign-on and federation is something that, from my perspective, and you can say I'm wrong, has been much more prioritised in the research community, again, because we love to collaborate and work internationally. And from an industry point of view, it's been less important, but with the advent of public cloud, it's gained more importance suddenly. So for example, you can have your own identity provider in your on-prem environment if you wanted to, with your accounts for your users and passwords and everything, but then link that with resources that are secured in a public cloud. So you have a way of separating those two concerns out. I've gone backwards.
Yeah.
Oops, sorry. Yeah, so I think with Optorad and other things we've been doing, we're really excited about the use of container technology. So for those who don't know, it provides like a lightweight encapsulation of an application and all its dependencies on an operating system. So it's like a lighter weight version of virtualization. And so it can provide an abstraction layer for interoperability. We've been doing some work looking at how that might help us with moving between different cloud providers and using containers as our common denominator for those environments. We want to extend the cattle side of our compute on cloud. I think this pets and cattle, have you come across that? I think it was I think it was coined by CERN. Is it CERN? Yeah, it's CERN. So you've got machines that you really want to look after and stroke and give little treats. Those are like your web servers and long-running services. And then you have your cattle, which is just your batch compute, which you send to slaughter. Okay, you just run it to as long as you want. So I think with container technology, these orchestration technologies, these ways of managing multiple containers is really important. We have used Swarm with Optorad, but we're looking a lot at Kubernetes from Google. It's open source, where we think it's got a lot of potential for us at the moment, but it's still an open question where we go with that. So, in terms of compute and analysis environments, there is a real need, I think, for us to move further into this space. So, extend the work with Jupyter Notebooks, look at using things like Dask, build on the work that we've done with the JASMIN analysis platforms. The JASMIN analysis platform is like a bunch of libraries and tools together in a set of packages, RPMs, that are useful to our community, okay? So for Earth observation, climate science community. So we'd really like to extend that, use things like Conda. We've been doing some work with the Met Office. We're looking at pipelines for creating those kind of environments. And then, as I say, training. I think unless we have the training, none of these good things are going to get actually used and exploited. That's me just about finished. There's some more information there. I'm going to do a cheeky plug now for another event, which is Cloud Computing for Research workshop on the 29th of November. It's at the Crick Institute in London, and there's a link there if you want to go and register for it. We've got about nearly 90 people registered so far, so it's great, but there's room for more. And we've got Kenji's coming along. We've got Amazon, Brendan's coming. And Google are coming, and there are lots of examples of use of cloud computing for research from many different domain areas. So like particle physics, bioinformatics, climate stuff, all kinds of things. So do come along.
Thank you, Phil.
All right.